Uh, Hello. So here in this video, I want to just give you some help in this lab. So in this lab, you will study the transit response of RC circuit as we explained in the lecture. If this is the standard, if this is the standard circuit, this is the formula you have to use here. That's what I explained in the lecture, okay? And in order to use this formula, I need to calculate three values. Number one, tau, which is actually equal R times C. Okay, this is R and this is C. Also, I need to know V naught, which is the initial value of the voltage before disturbance happened. For example, here the switch was open, there was some voltage here, whatever this voltage is V naught. And then when the switch is closed, okay, so one of two things should happen. If Vs is greater than V naught, so actually capacitor is gonna charge, or if V naught is greater than Vs, the capacitor is gonna charge. Disturbance happens, okay? So you need to know what is the initial voltage here for the capacitor. Also, you need to calculate the supply voltage with Vs. You need to know it, which this one here, okay? As I said in the lecture, if the circuit is not in the standard form, for sure, you can make it in the standard form by calculating a Thevenin circuit for the circuit connected to the capacitor. At this time, this should be R7 and this one should be V7. So here in the equation, this one should be R7 and this part should be V7. Okay. Let me come here. Yeah, so here in this lab, what you are gonna connect these two circuits, okay? The difference between the two circuits is the way we are gonna make a disturbance, or the way we're gonna make transit. So here in the first one here, we are gonna use a square wave like this one, okay? So disturbance here is gonna happen by changing the voltage. So we're gonna use it 0 volt and 4 volt. So when the supply is 4 volt, okay, so it's for sure it's gonna take some time until the capacitor here becomes 4 volt, okay? And then once we make a transition from volt to 0 volt, so the capacitor should discharge. So here again, what I want to see here in the first circuit, the circuit you are seeing here, we're going to make disturbance by changing the voltage of the source here. In the second one here, as you see, okay, I'm not going to change the source, but here I'm going to make disturbance by changing the configuration or the connection of the circuits, okay? So by opening a switch, closing a switch. So let's start with the first one first. So in the first one here, guys, it's very simple. All what you have to use, just use R. You have to use C, capacitor C. And then also I give you R here. Let's see what value for R. So here R is actually 270. So 270 ohms. Okay. And then C here is actually 220 nano farad. Okay. And this one should be a ceramic capacitor, so you don't need to worry about polarity. Okay. One more important thing here, when you connect the function generator to the internal resistance of the function generator, 50 ohm. And because 50 ohm is somehow closer than 270, so if you just ignore it, so the results are not going to be accurate. Okay. So that's what I told you before when you had a voltmeter. When you had a meter, all these devices you are using, they have resistance. If you just ignore the resistance, sometimes it's okay to ignore resistance when the internal resistance here is much bigger than this resistance, but in this case it's not much bigger. Okay, so if you ignore it, you are not going to get accurate results. That's why here when you do the calculation here, you have to add these two resistors together. So it has to be 270 plus 50 plus this internal resistance here. Okay, again, I just mean maybe because some students may be confused. I did not put this internal resistance. It's already in the function generator itself. So okay, so I did not put it in. I put this one, but I did not put it. But I have to consider it because it became a part of the circuit. So here I give you some interesting figures here, as you see here. So so in this circuit, if you have now tau, which is equal to R times C. And as I told you in the lecture, 5 tau is the time to fully charge or fully discharge a capacitor. So now, if 5 tau, if the time here, if this time is enough, so now I want to compare between this time, I'm going to call it T on, and between 5 tau. So I'm going to show you in this figure 3 cases. The first case when 5 tau is smaller than T on, as you see here. So what's going to happen in this specific use, if I just use these numbers here, 5 tau I think equal 1 millisecond, but T on is 2 milliseconds. So that's why here you see the capacitor is going to fully charge after, I think here this one, after this one here, sorry, this one is 1 millisecond, but the time here, the time is, let me see how, so here in the first case, so it's only, the tau is 0.1, 5 tau is 0.5, okay? So here, so that's why you can see after 5 tau, which in this case 0.5 millisecond, in the half here, it will reach to saturation. Same thing, so here this is 4 volts, so now the circuit is at a steady state. And then at this moment here, we are going to change the input to make disturbance, okay? So same thing, you can find here, we are going to go to 0 almost at 0.5 millisecond, which is actually 5 tau, okay? This is one case. However, if I change the frequency, as you see here, here I'm going to change the input, so I'm going to change here tau. But in this lab, you can also change the frequency, because again, we are comparing between this time here and between 5 tau. Okay, so the second case here, you can see 5 tau here, 5 tau is equal to, I think, 1 point. Let's see here in some numbers. 5 tau is 1.665. Okay, that means I need 1.65 millisecond in order to reach to a steady state. Okay. However, the signal here is only one millisecond. So here, this one has to continue until so it has to take more time. So it's gonna, this is 4 volt. So it needs reach to 4 volts. That's why what happened here, this voltage is not 4 volts. Okay, because this one here, we have here 1.60. It needs more time, okay? And then here, I'm gonna discharge. Same thing, I'm not gonna go to 0 because I did not keep it for enough time, okay? Even if you make 5 tau much greater than T on, you can see how the signal here looks like, okay? So, so as you see here, guys, we need 5 milliseconds using these numbers. If you calculate 5 tau, you will find 5 tau 5 milliseconds. That means after this one is gonna go here at this moment here. But because I'm gonna change the voltage, so the capacitor is not gonna reach to steady state. It's not gonna go to the steady state value. Okay. So and now it's gonna discharge this way. One very important thing, because we are going to use in this lab, as I told you in the lecture here, guys, if you just use the equation, again, this is from the equation we have here from the math, you can find here something very interesting. You can see after tau, actually the capacitor voltage will reach to 0.632 Vs. So that means the increase here from 0 increase only after 1 tau. It's going to be 63% after 1 tau. Okay, and then after 1 more tau, 2 taus, it's going to be 0.8. Okay, after 3 taus, it's going to be 0.95, and then after 4 taus, okay, after 5 taus, it's going to be so in this case, Vs equal 4 volts. That means after 5 tau, it should be 0.993 times 4 volt. That's why I told you we consider that after 5 tau, it's already fully charged. It's not for sure fully charged because still it needs 0.007. Okay, so it needs a very small amount of voltage, and to fully charge, it needs an infinite number of taus. That's why we consider that once it is 5 tau, it is fully charged. Okay. Why this is important? Because one part of this lab here, I want you to do 2 things. Number one, I'm gonna ask you to calculate tau. Number 2, I'm gonna ask you to measure tau. Okay, experiment in your experiment, I will ask you to measure tau. So how can you measure tau? Very easy. So all what you have to see here, you see what time, how much time it needs for the capacitor, how much time it needs for capacitor to increase, okay, by 63%. Okay, so if this one is gonna go to it's gonna go up to here 4 volt. So that means the voltage here has to be 0.632 times 4. So all what you have to do, I need to calculate the time from 0 until the voltage reach to this value. Okay. By the way, you can calculate it from charging and also can calculate it from discharging, because we have the same thing here in discharging. What's going to happen here in discharging, we're going to start from 4 volt. For example, if it is fully saturated. So here I'm talking I'm not talking about this case or that case. I'm talking about if you charge it until 4 volt and you discharge it until 0. Okay. So here we're going to start from 4 volt and then we start from 4 volt and then discharge it until it becomes 0. So yes, you can use this curve also to measure tau. All what you have to see here again, the change here is going to be 63%. That means this value here has to become 0.368 times 4 volt. Okay, so see what value here, and then this is the time here will be tau. See how much time it needs for the capacitor voltage to decrease from 4 volt until this value, and this will be your tau. Okay. One more interesting thing you can learn here. This is actually, so now you are going to measure tau, you are going to calculate tau, and you compare between them. One more thing interesting you need to know. So because I already know tau equal R times C. This is a way to measure the capacitance practically. Okay. So for example, if you have a capacitor, and I don't know what is C, I don't know the value of C. So I can connect it to a resistance and I can connect it to a source this way. And then I will calculate tau practically here. And I know I can do experiment to calculate tau. I know tau equal R times C. Okay, so now I can measure tau. I or no C, I can measure C, or I know C. So what I do here is a capacity. Sorry, I can measure R. So what I do here is a capacitance. So by this way, I can measure the capacitance. So this is also one way to measure capacitance. And here in the experiment, I'm asking you to do that. Okay. This is for the first part. Let's go to the pre-lab here for the first part. I want to make sure you understand before I go to the second part. So here I'm asking you here in this one here. Let's go to the pre-lab first. So here in the pre-lab, I'm asking you what to do here. In the pre-lab here, number one, you need to calculate the time constant. That's easy, right? Because you have, but you have to take also the internal into account, the internal resistance of the function generator. Okay. Number two, I want you to compute the voltage across the capacitor and also the current as a function of time when it charges from 4 volt and the initial is 0 volt. Okay, so here the capacitor is gonna start from 0 volt and it's gonna all the way until 4 volt. Is that okay? So now again, from what I taught in the lecture, you have already a formula for voltage and also have a formula for current, for the capacitor current. And okay, this is here in this lab I put only the formula for the voltage, but you have the formula. Let me go back just to make sure you understand what I'm saying. So if I come here, yeah, this is the formula, okay, for the standard circuit here, because this circuit already in the standard form, but I just need to add these two resistors together. I can just use this formula. Okay. However, to use this formula, I need to calculate three things. I need to find tau, I need to find the initial voltage, also I need to find Vs. So in this specific case, all what you have to do here is, let me come here. Yeah. So here, I give you the initial voltage, which is 0. Tau, you already calculated tau, okay, and the supply voltage is 4 volts. Using these three values, you can find the capacitor voltage as a function in time. Same thing, also you can find the current voltage as a function of time. Okay. This is for the first part. For the second part here, I want you to calculate the voltage. This is for discharging. So in discharging, the capacitor is going to start from 4 volt and it's going to discharge. Here the capacitor is connected when the function generator with 0 volt. So it's like your source is 0 volt, and then you have R, you have here C. The capacitor is going to discharge. Again, in order, you can use the same formula, but you need three values. Number one, you need tau, which is actually the same tau you calculated here because I did not change R or C. Okay. Number two, you need to find the initial voltage, and in this case, the initial voltage is 4 volt. Number three, you need to know the supply. Here in the supply voltage is 0 volt. So using the three values, you can easily calculate the during. So now you need two equations. This is the part that may confuse some students. I need two equations. I need one equation for because this is a different case, right? I change the supply. So here, yeah. So here I need equation for this part here, from here to here, this part. So here this is one equation. The first equation. The second equation you need to get it for this part. Okay. So this is the first part. Should be very easy. You need to calculate two equations. This equation should give you the voltage of the capacitor as a function in time. Let me see here. Next one here. Okay, next one here, I want you to find, this may be a little bit tricky, that's why I want you to pay attention to it. So here, what I wanna do here, guys, is, let me go back here. So for the second part here, I'm not gonna leave the capacitor to fully charge to 4 volt. I'm not gonna leave it to charge to discharge to 0. Okay, I want to do something similar to this figure here in the second part. I want the capacitor to charge until 3 volt and discharge until 1 volt, and then from 1 to 3, 1 to 3, 3 to 1, and so on. Okay, so all what so here, number one, you need to find the equation here, and you need to find the equation here. Okay, why is this equation now different? No, it's not the same equation I used to before, simply because yes, you have the same supply, BS is the same, but initial voltage will be different. Here, in this case, I start from 0 and I will go all the way until 4 volts. So here from 0 to 4 volt, here from 4 volt to 0. So it's because the initial is different, now we have a different equation. So how can you calculate the equation here? Again, all what you have to do to calculate the equation for charging, let's start with the charging first. For charging, again, all what you need to know, number one, you need to know tau, which is actually the same tau, because tau depends on, I did not change the circuit, so still the same tau, okay, I used before. Number two, the initial voltage here should equal to 1 volt, because we're going to start from 1 volt. Number three, the supply is the same. I did not change the supply. The supply is 4 volt, okay? Yes, it's not going to go to 4 volt, but the supply is 4 volt. You see what I'm saying? So using these three values, you can easily get the equation here. Is that okay? This equation, listen to me, this equation should give you the voltage of the capacitor as a function in time. So now I have an equation, V capacitor should equal whatever function in time, okay? So if I put time 0, I will get this value here. So if I put time whatever, so here I'm asking you find in this part, after you get the equation, you need to find what time here. What should be the time here? Okay, to go to 3 volt. So all what you have to do here, guys, you can say that V is a capacitor voltage equal to 3 volt, and then you can find T. Okay, so again, after you have the equation, whatever how the equation looks like. So now I have equation if function in T. Okay, so all what you have to do now, I'm gonna see what time. So I don't know the time. At what time the capacitor voltage will be 3 volt. Okay, so now I can, by this way, I can calculate this time. I can do the same thing here in this charging, and I can calculate this time here, this time. Okay. How can you do that? Again, in order to, you need to find the equation of discharging. The equation of the discharging, number one, tau is the same. Number two, the supply voltage equal to 0. Number three, here the very initial is 3 volts. So I'm gonna start from 3 volts. So using these three values, you can find the equation of the capacitor as a function in time for discharging. Okay. So again, the same thing. I want to know how much time it will take for the capacitor so that the V capacitor becomes 1 volt. All what you have to do here, I'm going to put here in the VC 1 volt, and then I can calculate what time is that. Okay, guys? So now, once I have this time, and once I know this time, I can calculate the total time, which we call it a period, the period from here to here. So this time should equal T1 plus T2. This time here is T1. This time here is T2. Okay. And once you have this time period, you can calculate the frequency of the signal. So frequency should equal 1 over T1 plus T2. Okay. This is by calculation. I want you to do the same thing using experiment. So what you have to do here, using experiment, you have to change the frequency of the signal. So it's an input square wave. You have to change the frequency until you see the capacitor voltage changing between 1 volt and 3 volt, 1 volt and 3 volt, and then you need to compare this frequency to the frequency you calculated. This should be somehow close to each other. There may be some small differences, but okay. but it has to be very close. Okay. So again, now you need to calculate the frequency, and also you need to measure it. Frequency that is going to make the capacitor charge between from 1 volt to 3 volt. Okay. Let me go see here if anything is missing in the pre-lab. Okay. I think that's what I'm seeing here in this part. Okay. So you need to find the frequency here. Let's go to let's go to here. What just I want to make sure everything is very clear. So what I'm saying here, guys, you don't need to worry about this one, because if you use a ceramic, and I think here you need for this value for 220, I think nanofarad, it's going to be ceramic anyway. So here what I'm saying, you need to change the frequency until you see it is 1 volt and 3 volt. Okay, and then also you have to measure the time constant here. Okay, you have to increase the frequency, determine that transit here, the capacitor should change. So here, okay, so here actually, okay, there are two parts here. One part here, you have to make sure is the figure here will be similar to the first figure you have here, which you should have enough time. Yeah, so the figure will be similar to this one here. Okay, so you have to increase the frequency. You have to increase the frequency until the capacitor reaches to steady state. Is that okay? Because, and then using this figure, experimentally, you need to measure tau. Okay, so make sure it's gonna go to steady state here, and it's gonna go to it doesn't. The figure may not be identical to this one. I don't care. It doesn't need to be identical, but just make sure the capacitor is gonna go to steady state, and also it's gonna reach to 4 volt, and it's gonna go to 0 volt. Okay, so increase the frequency or decrease it. So you need to change the frequency until you see something like that, and then you can calculate tau. In the second part, you need to change the frequency until you see something like this one, and you need to make sure the signal would from 1 volt to 3 volt, and then you need to calculate what was the frequency here, and you need to compare it to the value you calculated. Okay. Let's see if anything else you need to do here. No, nothing. I think that's all what you need to do. Okay. For the second part here, for the second circuit here, for the second circuit here, we're not going to use the scope. We're going to use the digital, the voltmeter. We're going to use the voltmeter to measure, to watch or to monitor the capacitor voltage. Okay, so the idea here, as I told you, the input here is going to be a DC value. It's not a square wave. So disturbance in the very beginning, I'm going to close the switch. For sure, you don't have a switch. Instead of a switch, just a wire. If you so make sure you connect this wire. Okay, you need to wait for some time until the capacitor becomes at a steady state, until the voltage here reach to a steady state. Okay, so as I told you in the lecture, if this circuit is in a steady state, so here you need to calculate the initial voltage here. How can you calculate the initial voltage here? You have to make the capacitor here open circuit, and then after that you calculate the voltage here. This one should give you the initial voltage. Okay. After that you need to open the circuit, and then now the capacitor should be either charged if the Vs is greater than the initial voltage, or V naught initial voltage, or maybe the capacitor is going to discharge if the initial voltage is bigger than Vs. Okay, and now here, because I'm not going to use the scope, I'm going to use voltmeter. So you need to connect the voltmeter here. Okay. Here, I'm gonna make sure R1 times RC is a big number. So I'm asking you here to select tau equal R1 times C. It has to be 12 seconds. Why is a big number? Why 12 seconds? Just to give you enough time to just see the value of the capacity of the meter here. Okay, so that's why I'm gonna make it. You need to select R1 times RC to be 12 seconds. Also, I think I asked you to select R2 to become half of R1. Okay, so all what you have to do here, but there is a trick I'm gonna talk, or there is a small problem I will talk about. Okay, so all what you have to do, you have to select some value for R1, you have to select some value for C, so that multiplication here equal to 12 second. Number two, R2 here has to be half of this one. So in the pre-lab, I'm asking you, in the pre-lab here, I'm asking you to, number one, to calculate, let's go to the pre-lab here to see what I'm asking you to do. So here in this pre-lab, you need to find the equation of the voltage as a function in time. Is that okay? When the switch opens. So again, in order to find this equation, you need three values. Okay. Number one, you need. Let me go back here to show you what I need. So just use the equation. You need three values. So when you open, okay, when you open. ايوه يا بابا، ايوه يا بابا، ايوه حبيبتي. ايه يا بابا، في ايه بس؟ اوكي. اسمه ايه ده؟ انا عملت دليفري بسوبر ماشي. طيب. اسمه ايه ده؟ دي يعني عيادة يعني فتحت الشقة وسبت الباب يعني so I can يعني اشد يعني في الاسانسير ماشي. طيب. طيب. الساعة 11 فتحت الشقة فتحنا كلنا. اعمل ايه؟ يعني انت واقفة قدام باب الشقة؟ طب الخدامة موجودة؟ مش موجودة. طب انت مش معاكي المفتاح تنيمة يعني؟ مش معايا المفتاح، انا نايمة. طب انا اعمل ايه، اكلمها يعني ولا ايه؟ خلاص اقول لها معلش الباب قفل على كده، دي راح بس تجيب دليفري. انت كنت فعلا بتجيب دليفري ولا كنت بتعملي حاجه ثانيه؟ لا فعلا كنت بجيب. طب خبطي على الباب انا هكلمها. ماشي؟ ماشي. اي ماما. معلش لينا كلمتنا بتقول لي ده هي جابت دليفري من الباين من السوبر ماركت، وبعدين راحت تشد الاسانسير او جايبه دليفري، فالباب قفل عليها. معلش ده ما هي قدام الباب على طول بتقول لي. هي خايفه تكلمك، خايفه منك تكلمك. ما اعرفش راحت تجيب دليفري ايه ولا تشد الاسانسير ايه. ماشي. عشان الدليفري. ماما ممكن ما اعرفش بقى يا ماما، معلش ما تزعلهاش بقى. ماشي. So as I told you, in order to get you need to find the equation after you open the switch here. So to find this equation, you need three things. Okay, you need the initial voltage, you need to know the supply voltage, you need to know tau, which is actually R times C. Okay, so this is Vs because once you open here, the circuit becomes in the standard form like this one here. Okay, so this is Vs is given to you here. And R1 you already should selected R1, so now tau equal R1 times C. So now I know tau, now I know Vs. All what I need to find is the initial voltage. And as I told you, for the initial voltage, once if you connect this one here, and you have to leave the circuit to be in steady state, and then you need to calculate the voltage here. Okay, you need to, and this will be your initial voltage. So using these three values, you should be able to find once you open here, you should be able to find VC as a function in time. Okay. Let me see else what else here I ask you to do in the pre-lab. So here the switch is for the initially I'm telling you here, then it shows the value of R1C available in your, so that's what I'm telling you. Try to find some values for R1 and C, so that the multiplication of R1 times C is actually 12, okay? And then set R2 to be half of the value of R1, and Vs is gonna be 10 volt all the time. And then what you have to do here in this lab, you need to fill up, what you have to do here in this lab, you need to fill up this table here. So what should happen is that you need once first of all you need to connect the switch, okay, and then keep it for some time, little 1 minute or so, some very little bit time, okay, just to be in a steady state, and then you can just open the switch, okay, again, because you don't have a switch, you can just make a wire and just take the wire off, and then you need to monitor the voltmeter and see what is a time when the, here every, you know, tau is equal to 12 seconds. Is that okay? So here you can make it this one. So you need to find these values here for the voltage at every time. So here this one should be at time 0. This one here have 6 seconds, 12 seconds, and so on. Okay, because maybe 6 seconds is not enough. So you, okay, how can you do that? For sure you should have a stopwatch with you so that you can look at the stopwatch, and then you look at the voltmeter, see what is the value of the voltmeter at 6 seconds, 12 seconds, whatever. There may be another, and then you have to do it twice, okay? And there may be another way to do it. Just you can take a video. You can take a video for the voltmeter, and then after that you can run the video to see what was the voltage of the voltmeter at 6 seconds and so on. Okay. Once you do that, you need to measure tau. I told you a tau, tau should be a tau. You can see at what value the voltage should drop, as I told you, to 63%, or to increase or to decrease to 63%. Okay, and now once you can use the measured tau here, and you can use R1. You know, we already know that tau equal R1 times C. Okay, so you can use the value of the measured tau. You can use R1. Okay, you already know R1, and then I don't know the capacitance. Okay, you can assume you don't know the capacitance, and then you can measure the capacitance. By the way, the measured values for the capacitance may be different from the capacitance you are expecting. This, because number one, the temperature has an impact on the capacitor. Number two, capacitor also can be impacted by aging. So as the capacitor gets older, it's going to be difficult. Capacitance also is going to change. Okay. So, but everything looks okay now, straightforward. However, there is a small trick now. What is the small trick? The small trick, and let's see how can we handle it. Okay, there is a small trick here, and this is something you need to learn how how can you do it. Okay, so let's see. In the small trick here, guys, because you are gonna connect a voltmeter here. You are gonna put a voltmeter here. This voltmeter has an internal resistance which is 5 mega ohm. Is that okay? So as I told you before, guys, this 5 mega ohm may not have big impact when the value of the resistance are small. Okay. However, if this value of the resistor R1 and R2 are not small, so in this case, the 5 mega ohm, you have to take it into account. Otherwise, your calculated values are not going to be accurate. Okay, so what I mean is that, look here, guys. So actually, it's like you have here a resistance that's 5 mega ohm. Okay, however, if this R1 and R2, if you can make them like in the range of 100, because R2 has to be smaller than R1. So if I can make R1 in the range of 100, 200, something like that. So in this case, 5 mega ohm may not have impact, and I can safely ignore it. And then the calculated result, this will be very, or always there is an error, but this is going to be very small error, and should be accurate enough. Okay, so this is one case. Okay, however, to do that, because remember, R1 times C has to be 12 seconds. 12 seconds is a big number. So if you make R1 small, like 200K or 120K, or if you make it something small, so now you need to have a big capacitors. Okay, you may not have this capacitor in your kit, but still you can connect. For example, you can find 2 capacitors. For example, if I need to make like 500 500 microfarad, for example. So, but I don't have this number. Still, you can connect two capacitor parallel. Okay, so this one can be 300, this can be 200. Okay, guys. So one way to do this experiment, number one, try to make sure R1 and R2 in the range of between, for example, 100 to 200 in this range. Okay, so that in this case you can just ignore the 5 mega, because 5 mega comparing to 100, 200 is going to be nothing. The error will be too small. Okay, you can ignore it. But in this case, you need to find the big capacitance, because the multiplication has to be 12. This is one case, okay? What you can do here, another case, what you can do here, if you don't want to make it this way, for example, if you select R1 here, it's going to be like something like 1 mega ohm or something like that. Now you have to take into account R, because now this will have impact in the circuit. So the question is that how can you take it into account when this resistance is close to these two resistors? It's not like much bigger. Okay. So in this case, what's gonna happen here? It is like in your circuit, you have additional resistance here, R internal. Okay. That means when you calculate at a steady state, when you do the calculation at a steady state and you make this circuit short circuit here, you make the capacitor open circuit. So at this time now, so here you have here R1, now you have R2, and then you have a resistance here 5 mega ohm, okay, this way, and then plus minus, and then the capacitor is here. So you need to find the voltage across the capacitor. You need to find the voltage across the 5 mega ohm. Is that okay? You remember, if you in the video here, if you go back what I explained, you can remove this one and you can make it this way. If R1 and R1 are much smaller than 5 mega ohm. This is when when I open the switch. When the switch is open, when you open the switch, now again you are still, this resistance will be there, right? So now what I said here, you have R1, you have a capacitor, and then here you have R internal, okay, and then you have here VS, okay. So again, if R1 here is much bigger than R input, so you can just ignore R input, because all the current will come here. It's going to have very little impact. However, if it doesn't have a big, if you want to, if they have somehow close, and this circuit is going to load, this R input is going to load, it's going to make load to the circuit. So that's okay. So you can consider it in your calculation. So the way you can do it now is, so now the circuit looks like you have here R1, you have here R input, and then you have a capacitor this way, okay? So now, and here you have VS. So now the circuit is not in the standard form because of this R input here. So you can easily make it in the standard form. So you can calculate here R7, and you calculate here V7, and then capacitor C here. Okay, this time you can find R7 equal to R1 parallel to R input, and then you can find V7 equal to VS times R input divided by R internal plus R1. Is that okay? And then by this way, I consider the internal resistance. By the way, you can see right now, if R internal much bigger than R1, so actually these two together, this ratio becomes very close to 1. Okay, so that's what I told you. If the internal resistance is much bigger than R1 or R2, it's gonna be accurate to just ignore this resistance. Okay, same thing here. If you have R1 parallel to internal, and here R1 is much bigger than R internal, the calculation R7 will be very close to R1. You see what I'm saying? So again, in all cases, you are gonna have error. Okay, in all cases. However, this error, we can ignore it. It should be accurate enough if this internal resistance is much bigger than R1 or R2. So again, guys, I will leave it this one for you to decide. Should you take into account R input or not? So this based on the value of R1 and 2. If you select R1 and 2 to be like much smaller than R internal, you can just ignore it, but it's gonna make a very small error, but which is okay if you have a small error, but the calculation will be easier. It's okay. Or you can take R input in, if you want to make it very accurate, you can assume you are gonna have a resistance here, we call it R internal, and then you have to take it in your calculation. Anyway, I think that's all what I want to say here. Let me see if I have anything else. I think that's all. Okay. Focus and try to, yeah. Thanks so much. Bye.